Good morning. Last day I mostly completed the assumption part. Only I need to mention about the notion of linearity in context of econometric exercises. We are typically talking about classical linear regression model. So we need to understand what actually the term linearity indicates. Before that, any question regarding the assumptions we discussed? Expectation of EY is equal to 0, variance, a constant, which we are calling homoscedasticity assumption. Third assumption we made, that is the assumption of non-autocorrelation, that is two errors are not related to each other. Fourth assumption we considered covariance between xi and ey that should be equal to 0. This is the requirement of linearity. In the right hand side, there will be no interrelation among the variables. This is typically a two variable analysis, and naturally, therefore, there are two variables only in the right hand side, the explanatory variable xi and the error variable, random error component ey. So there should not be any relation between xi and ey, and for that matter, we are considering covariance xi ey is equal to 0, and while we are considering this kind of interrelation, we are sticking to the linear relation because we are trying to frame classical linear regression model. Fifth assumption we considered, that is the assumption of normality. Error is normally distributed with expectation of ui is equal to 0 and variance of ui a constant. I mentioned that the first four assumptions, that is the unbiasedness assumption, homoscedasticity, non-autocorrelation, and the covariance between xi ui is equal to 0, these four assumptions we need for estimation purpose. The fifth assumption, that is the assumption of normality, is not required for the estimation purpose as long as we estimate the parameters using the least square technique. Fifth assumption is required only when we will move for hypothesis testing exercises. Apart from these assumptions, there are several requirements as well. The most important requirement in context of framing this kind of regression model is there should not be any outlier. In this context, I mentioned that the kind of regression modeling we are doing, that is the mean-centric approach, conditional mean modeling. And for that matter, if there is any outlier, the estimated model will be an erroneous model. And for that matter, we have to remove any outlier if there is any to begin with. Okay, so before considering the regression model, actually we need to check all these things, whether there is any outlier. If there is any outlier, before framing the regression model, we have to remove it, because the kind of regression we are discussing here, that is a conditional mean modeling approach. So I think I completed up to this in the last class. Any question in this part? Anyone, any question? Is this okay to all of you?
Yes, ma'am.
Oishi?
Yes, ma'am.
It's fine? All the assumptions, everything fine?
Yes, ma'am.
Oishorjo?
No, ma'am, it's fine.
So let me tell you something about the notion of linearity we will consider in case of this kind of parametric regression model. Last day, I mentioned about this term parametric and non-parametric approach. The kind of statistics and econometrics we are developing at undergraduate level, this approach is a parametric approach. In case of parametric approach, in the background, always there is an hypothesis. That is, there is a model in the background. And on the basis of empirical investigation or the data, we try to judge whether that idea, that model, that is right or not. So in our mind, there is a setup, and we are trying to check whether there is any issue regarding that setup. Okay. Last year I mentioned about we are very happy with the random sampling and normality kind of thing. So if I find that my data set is not normal or somehow it is not random, we try to handle the things or the database in such a way so that we can establish the normality and the randomness. Okay. Because randomness will ensure from this sample, whatever we will conclude, that will be perfectly applicable to the population. And if everything is normal, the data set is normal, it follows normal distribution, then also we can reach to several fine conclusions, and for that matter, there will be no issue regarding the background work of CMM kind of structure, conditional mean model. So we are very happy with randomness and normality kind of things. So when there is a model in our mind and on the basis of the data, we try to judge whether that idea is correct or not, or this kind of model building exercise we prefer. This approach is called parametric approach. However, parallel to this parametric approach, the modern econometrics mostly concentrate on non-parametric approach. There is no parameter to begin with. Okay. There is no population value, and on the basis of the sample we are trying to reach at that population. The idea is not like that. So from the data we will learn what can be the pattern of the relationship among the variables. Okay. So that approach is called the non-parametric approach. However, always we start with the parametric approach and then we move towards deviation, and this makes the entire reading process more acceptable, because we have started from a core subject economics, and then we are learning some statistics, then we are learning econometrics to judge our core idea, core modeling. Okay, so the way we are trying to develop the things, we are a bit comfortable with that, because directly if we start talking about the data, it will be difficult for us to relate the things with the basic knowledge of economics. Okay, so now I'm rereading the sentence once again. Linearity of a parametric regression model indicates that the model is linear in parameters, not in variables. The model is linear in parameters, not in variable. Okay, this is very, very important. Okay. We are telling that model is linear in parameters, not in variables. Okay, not in variables. That means if I write a framework yi is equal to alpha plus beta xi plus gamma xi square plus delta xi cube plus ui. This model is linear. This model is linear because alpha, beta, gamma, delta, these are the 4 parameters of the model, and the model is linear in 4 parameters. Whatever power is appearing, that is the power with respect to the variables, xi square, xi cube, etc. So if I look at this equation econometrically, then this equation is linear, because the concept of linearity is the model should be linear in terms of parameters, not in terms of variables. It can be linear in terms of variables, it may not be linear in terms of variables, okay? So if I get this kind of polynomial with the power along with the variables, in that case, the model is considered as a linear one. Or if the model is this is also a linear model, okay? The idea is, under most of the circumstances, if I consider non-linearity in terms of the variables, if we go for logarithmic transformation, the model will become linear. Okay, if we consider the logarithmic transformation, we will get back linearity. Okay, so some kind of transformation always, if it is in terms of, non-linearity in terms of the variables, in that case, some form of transformation help us to get the linear structure, and in that sense we will consider all these kind of framework as linear regression model. So in context of economics, the nonlinear function, we consider, that is the cost equation, production equation, etc. Cost, production, these are the cubic functional forms. Okay, so we get the S-shaped curves, inverse S-shaped curves, or if you consider the average product curve, average cost curve, U-shaped curve, inverse U-shaped curve, So all these equations are basically linear to an econometric framework. So whenever we are telling that we are estimating the linear regression model, therefore, don't think that we will be able to estimate only the linear demand and linear supply or linear consumption function or linear investment or savings functions. We will be able to estimate all the functional forms we discussed in context of micro and macroeconomics. Because if you look at the equations, all these equations, when we consider the non-linearity, S or U, inverse U, all these functions, these are, non-linear in terms of the variables. So when we will consider all these model building exercises in terms of econometric analysis, all these models appear to be linear in terms of parameters and therefore fully estimable. So all functional forms we discussed in context of micro and macroeconomics fully estimable using this kind of classical linear regression model framework. The kind of model which we will consider as non-linear in context of regression model is given by, say, or these models are non-linear. Okay, so yi is equal to alpha square, or in the next model alpha square e to the power beta, or if you consider beta cube, some power of beta alpha. So if you consider the model in this way, in that case only the model will be considered as non-linear, and the estimation technique today we will learn will not be applicable for this kind of non-linear model, because we are framing classical linear regression model. Okay, linearity is a good starting point, and what we are finding that the models are linear in terms of parameters only. It can be non-linear in terms of variables. Therefore, all the models generally we discuss in context of economics can be captured or can be estimated using this kind of regression framework. Okay, any question? Any question regarding the idea of linearity? Okay, so when we will discuss the numerical exercises both in Johnston and Donado and in the book by Madala, you will find several functional forms and you need to identify which one is linear, which one is non-linear. Okay, so in that case, please keep in your mind, if the model is linear in parameters, then it will be considered as linear in our case. It can be non-linear in terms of variables, doesn't matter. It should be considered as a linear construct. However, if there is some non-linearity in terms of the parameters of the model, in that case, the model will be considered as a non-linear model. So keeping these points in our mind, next we will move towards the notion of estimation. Okay, we will move towards the notion of estimation. Our regression model is given by estimation means, we have to estimate these two unknown parameters of the model. We have observation on yi, we have observation on xi. On the basis of observations on yi and xi, we have to estimate these unknown parameters of the model. And then we will get the estimated model. Okay. So what actually we are doing? We have from the reality, we are getting this. The values having the two coordinates xi and yi. So in reality, from reality, we are getting this kind of observations on xi and yi. If price is 2, what is the demand? If price is 5, what is the demand? So in this way, if rate of interest is this, what is the savings? So we are getting this information from the reality, and then we have to estimate the savings equation or the demand equation or the supply equation, etc. This means basically we have to estimate the unknown parameters alpha and beta so that we can generate a fitted line. This line is the fitted line or the estimated line. So this line is basically yi hat this one. This is the estimated line or the fitted line. Okay. So today we will learn how from the observations we can reach to this fitted line. Now, when we started the entire exercise, we mentioned that from reality, we are getting observations and we have some population regression in our mind, or we have expected value of yi in our mind. Population regression or expected value of yi in our mind. So the gap between the observed value and the actual or the expected value, that we are calling the random error. Okay. In other words, we defined ui as yi minus expected value of yi, or this can be written as yi minus y. This is the population value or the expected value of yi. So this is the population regression, and this is the actual thing we are getting from the reality. So the gap between the observed and the exact, or the gap between the observed and the expected, this is called the random error. And the natural idea which emerges from this concept is we have to minimize this random error if we want that yi should be very, very close to that of expected value of yi. What we are expecting, if the observed one we want should be very, very close to that, that means we have to minimize ui counterpart. We have to minimize the random error counterpart. However, there is a problem with this random error ui. UIs are not observable. UIs are not observables. Okay, because expected value of yi, or the population value y, or the exact functional form y, which is alpha plus beta x, this is not observable. Yi, that is the observations we are getting from reality, this part is observable. However, this part is not observable. Exact functional form is not observable. Okay, or the population counterpart is not observable. Expectation of yi is not observable, because all these things are alpha plus beta xi. Since alpha and beta are unknown, therefore expected value of yi or exact value of y, these things are not observable. As a result, the difference between yi and expectation of yi, which is ui, is not observable. So if ui is not observable, we cannot frame a minimization exercise considering this random error ui. So we have to find out some sort of estimator of ui which is observable. If we really need to minimize the error counterpart, we need to develop some concept by which we will be able to capture ui. And if that concept is observable, we have to minimize that concept only. So ui we cannot minimize. So we need to develop a proxy for ui, or you can say an estimator for ui. Okay. Now in this context, we develop the notion of residual. Now what is residual? Residual is the difference between the observed and estimated. This yi is the observed, while this is estimated value of y. Okay. Now, estimated value of y, that is yi hat, is observable because it is alpha hat plus beta hat xi. It is not alpha plus beta xi, rather it is alpha hat plus beta hat xi. So what is yi hat? Both alpha hat and beta hat are observable, and for that matter, yi minus yi hat, this is observable. The gap between the observed and the estimated is called the residual, and notationally, in general, we use the term small e to define residual. So ei is the residual. So whereas the gap between observed and exact is called the error, the gap between observed and estimated is called the residual. The interesting feature of EI is it follows that is expectation of EI is equal to 0, variance of EI constant, covariance EI, EJ, non-autocorrelation. It follows all the properties or characteristics of UI. And it is observable. It follows all the characteristics of EI and it is observable. So our minimization exercise should be based on this residual part. Okay. Instead of UI, while we will frame the minimization exercise, it will be based on EI, the residual part. Now, the regression model is, the basic regression model is given by this is our regression model. Okay. Here, instead of UI, we are bringing EI while we are moving towards the estimation process. Now, while we will think about minimization of EI, what we will do, we will not consider the direction of EI. As you know, some of the observations or some of the scatters will lie above the line, some of the scatters will lie below the line, you know. So we can consider these as positive discrepancies, whereas these as negative discrepancies, okay. However, when we will go for minimization of residual exercise, we are not interested about the direction of the residual, and for that matter, either we have to consider modulus values of EIs or we have to consider EI square. The practice is we will consider EI square of the residuals. We will consider square of the residuals, EI square, because we are not interested about the direction of the error term. One more thing is important. We will not consider first observation and we will minimize E1 square. Then second observation and then we will minimize E2 square, or in the similar fashion, the nth observation and then we will minimize En square. We will not move like that. Rather, we will consider summation I is equal to 1 to n EI square. We will consider summation I is equal to 1 to n EI square. Okay. So sum of squares of residuals we will consider. Okay. This is called RSS, residual sum of squares. Okay. Summation EI square is called the residual sum of squares, and you know, in general we call it RSS, residual sum of squares. So while we are going to estimate the parameters of the regression model, we will minimize these residual sum of squares, summation EI square, residual sum of squares. Any question?
Ma'am.
Yes.
Ma'am, why I had the expectation of YR point estimator though?
yi hat. Yi hat is the estimated regression model.
yi hat expectation of yi or point estimator तो.
Yes.
Okay, ma'am.
Yes. That you are estimating. Actually, you have some population concept in your mind, and on the basis of the data, you are doing that. Okay. So, expectation of yi is yi hat. That you can do, maximum you can do in your database. Any other question? Now here, please take a note. Okay. First, let me tell you what actually you need to take as a note. In general, when we go for any kind of estimation or we talk about any kind of estimator, we derive estimators for the parameters. In general, we do not derive or do not talk about estimators of the variables. We estimate the parameters in general, not the variables. However, in context of the regression model, although UI is a random variable, we are talking about an estimator for this, which is the residual EI. Therefore, this EI is called the some sort of estimator of UI. Okay, it is called the some sort of estimator of UI. Residual is called or known as some sort of estimator of UI. Why? Because in general, we estimate the parameters, not the variables. Okay, so when we are trying to place something which is an estimator for variable, not for the parameter, in that case, we will use the term some sort of estimator. Okay, so please take note. Residual within bracket EI is some sort of estimator of the random variable UI. Is a some sort of estimator of random variable UI. In general, we estimate the parameters. In general, we estimate the parameters, not the variables. Not the variables. And hence, for EI, we use the phrase some sort of.
Last line একবার repeat করবেন?
Hence, for residual or for EI, we use the term or we use the phrase some sort of, within inverted comma, some sort of. Okay, so as I mentioned, we will estimate today, we will learn how to estimate the parameters of the model and therefore how to derive the estimated relationship between Y and X, or how to derive the appropriate fit or appropriate line through the scatter points. Now here, to begin with, we will use the ordinary least square technique to estimate the parameters of the model. We will use ordinary least square technique to estimate the parameters of the model. Now, while we are estimating the parameters of the model, the question we are addressing is, how would we know that this fit is a best fit? Okay. Therefore, we are starting with the concept of residual EI, and we will try to minimize these residuals, to derive the best fit. How we will understand this fit is a good one, it is close to the population one. We have to minimize the error component of the model. Okay, and already I hope you understood, you will be not able to minimize the error component, and for that matter you are bringing some sort of estimator EI here, and our minimization exercise will be based on the notion of residual. Now, while we will go for minimizing these residual, as I mentioned, we will not consider EI, rather we will consider sum of EI square, which we are calling the residual sum of squares, RSS. So if you look at the last point, we are going to understand how we will minimize summation EI square. How we will minimize summation EI square. We have to minimize summation EI square in terms of alpha hat and beta hat. And these summation EI square is nothing but summation yi minus alpha hat minus beta hat xi whole square. EI is yi minus alpha hat minus beta hat xi. So summation EI square is given by summation yi minus alpha hat minus beta hat xi whole square. Okay. So we have to take the first derivative of summation EI square, or summation yi minus alpha hat minus beta hat xi whole square, in terms of alpha hat and beta hat. Solving the two first order conditions, we have to derive the values of alpha hat and beta hat. Now, instead of one explanatory variables, if I have a number of explanatory variables, then the model looks like yi minus alpha hat minus beta hat xi minus gamma hat, say zi, then another parameter along with that, another variable will appear. So we have to take minimization of summation EI square with respect to all possible parameters we have in the regression model. Since to begin with, we are considering a two variable regression model, simple framework, we are considering yi is equal to alpha plus beta xi plus ui. We have two parameters in our construct, so we will have two first order conditions. Solving the first order conditions simultaneously, we will derive the values of the parameters of the model. Okay, so in the next step, we will minimize summation EI square with respect to alpha hat and beta hat. In other words, we will consider del RSS by del alpha hat, and we'll set this equal to 0, and then del RSS by del beta hat, and then set this equal to 0. Del RSS by del alpha hat is equal to 0 will generate the first normal equation, whereas del RSS by del beta hat is equal to 0 will generate the second normal equation. And solving first and second normal equations, we will get the values of alpha hat and beta hat. Are you understanding the technique or what we are going to do in the next step? Any question? So everybody is understanding?
Yes, ma'am.
So in the next step, you need to derive and then you have to set these values to be equal to 0 by FOCs, first order conditions of minimization. So this thing you have to do. Take derivative of RSS with respect to alpha hat, set this equal to 0, take derivative of RSS with respect to beta hat, and then set this equal to 0. So now look at the equation. Just I'm telling you, and then I'll show you the entire derivation, and you will be able to do these things in fact on your own. Now, if I take derivative of these RSS with respect to alpha hat, we are getting 2 summation yi minus alpha hat minus beta hat xi, and then there is another minus sign. Okay, this will be multiplied with minus 1. So basically you are getting minus 2 into summation yi minus alpha hat minus beta hat xi is equal to 0. Now if you get this equation, since minus 2 is not equal to 0, basically and this is equivalent to summation ei is equal to 0. Everyone, can we write this equal to summation ei is equal to 0?
Yes, ma'am.
Yes, ma'am.
This is called the first normal equation. Okay, this is called the first normal equation. Summation ei is equal to 0. Okay, and from this expression, that is summation yi minus alpha hat minus beta hat xi is equal to 0, we will get summation yi minus n alpha hat minus beta hat summation xi is equal to 0. And if I rewrite the thing, I'll get alpha hat is equal to y bar minus beta hat x bar. Okay, I'm showing you the derivation, etc. within a minute. So once I get this part, I'll move to del RSS by del beta hat, that derivative part. So from this expression, if I take the derivative with respect to beta hat, what is the value we will get if I take the derivative with respect to beta hat? Anyone? If I take the derivative?
Ma'am, it will be minus 2xi times summation ei.
Yes. Actually, it will be minus 2 will remain outside the sum. It will be minus 2 summation yi minus alpha hat minus beta hat xi into xi.
Right, ma'am, right.
So basically, from the second equation, we will get something like this. Summation ei xi is equal to 0, which we will call the second normal equation. And we will solve this one and this one to get the values of alpha hat and beta hat. So this is the technique. So let's try to understand what actually will be the steps. So I think you have pen and paper with you. So I'll request everyone to solve these things. So first we are setting del RSS first order conditions. Okay, so give heading FOCs. First order conditions. So first we are considering del RSS by del alpha hat is equal to 0. Now RSS means summation yi minus alpha hat minus beta hat xi whole square. So basically del summation yi minus alpha hat minus beta hat xi whole square divided by del alpha hat is equal to 0. So if I take the derivative minus 2 summation yi minus alpha hat minus beta hat xi is equal to 0, this can be presented as summation ei is equal to 0, which is called the first normal equation. Summation ei is equal to 0. This is called the first normal equation. Moving to the equation, we can write the expression as summation yi minus n alpha hat minus beta hat summation xi is equal to 0. If I keep alpha hat to the left and divide the right hand side by number of observations n, we are getting the expression y bar minus beta hat x bar. So call this equation number 1. Alpha hat is equal to y bar minus beta hat x bar. Call this equation number 1. Is there anyone who has any doubt at any step in the first condition? So next, we are moving to del RSS by del beta hat is equal to 0. Del RSS by del beta hat is equal to 0. So first take the derivative minus 2 summation yi minus alpha hat minus beta hat xi into xi equal to 0. Since minus 2 is not equal to 0, I am considering summation yi minus alpha hat minus beta hat xi into xi is equal to 0 and rewriting that as summation yi xi minus alpha hat summation xi minus beta hat summation xi square is equal to 0. This can be presented as summation yi xi minus summation xi in the second term I am writing as n x bar. So it is n into alpha hat into x bar. Summation xi I am writing as n x bar. Minus beta hat summation xi square is equal to 0. In the next line, I am substituting equation 1 in place of alpha hat because I like to find out the value beta hat in terms of y and x. So I'm putting the value of alpha hat in the second term, which is y bar minus beta hat x bar. I replaced alpha hat by y bar minus beta hat x bar. So I have summation yi xi minus n x bar y bar. All beta hat terms I'm keeping to the right hand side. So I have basically in the left hand side plus n x bar square beta hat. So when I'm putting it in the right hand side, minus n x bar square beta hat. And there is another term, minus beta hat summation xi square, that also I'm keeping in the right hand side. If I take beta hat common, beta hat value can be presented as summation yi xi minus n x bar y bar divided by summation xi square minus n x bar square, which is equivalent to summation yi minus y bar into xi minus x bar divided by summation xi minus x bar whole square. These are the different forms. These are the different forms. Or beta hat is covariance between xi yi divided by variance of xi. It is covariance between xi and yi divided by variance of xi. In some books, you will get the notation so capital X. Okay, so you will get this kind of notation. These are only the notational matter. The main thing is how we are calculating beta hat. Okay, and by the way, from this line, we can write this is the second normal equation. Okay, this is called the second normal equation. Summation ei xi is equal to 0. This is called the second normal equation. So in this way, we get the values of alpha hat OLS and beta hat OLS. Alpha hat OLS is y bar minus beta hat x bar, whereas beta hat OLS is summation xi yi minus n x bar y bar divided by summation xi square minus n x bar square, or summation yi minus y bar into xi minus x bar divided by summation xi minus x bar whole square, or covariance between xi yi divided by variance of xi. Any question regarding any step or any issue? How we are estimating parameters of the model? Everybody got it?
Yes, ma'am.
So the final values we generally present as alpha hat OLS. Once you get alpha hat and beta hat, you are getting the estimated fit yi hat, which is equal to alpha hat plus beta hat xi. Alpha hat plus beta hat xi. Okay, so these first order derivatives gives us the first normal equation. Now you know that. Second normal equation, summation ei xi is equal to 0. And here there is an equivalence. What does summation ei equal to 0 means? You know, ei's are the residuals. And this, if summation ei is equal to 0, that means e bar, okay, their average, that is also equal to 0. So this is equivalent to the concept expected value of ui is equal to 0. Expected, that is the mean of error, is equal to 0. Okay. And the idea summation ei xi is equal to 0, that means there is no linear relationship between ei and xi. This is equivalent to the idea covariance xi ui is equal to 0. So summation ei is equal to 0 is integrated with the idea of expected value of the random error is equal to 0, whereas the second normal equation summation ei xi is equal to 0, that is integrated with the idea that there is no linear relationship between xi and ui. Okay, so already we did this thing. Now, in case of regression analysis, many a times we use the deviation form. Small xi indicates capital Xi minus x bar. Small yi indicates capital yi minus y bar. So if I write the equation in the deviation form, or if I write the expression of beta hat in the deviation form, this can be presented as summation small xi yi divided by summation xi squared 2, because summation or where small xi is equal to capital Xi minus x bar and small yi is equal to capital yi minus y bar. So these are the notational matters. So go through the slides, go through the text, go through the notes, you will understand all these notational matters. Once we derive the values of alpha hat and beta hat, in the next step, we have to discuss the properties of beta hat. Okay, discuss the properties of alpha hat and beta hat. First of all, whether we are the estimated values we are getting alpha hat and beta hat, these are unbiased estimates of alpha and beta. Question number 1. Question number 2, are these estimates minimum variance unbiased estimators? Okay, we are telling that on the basis of observations we are calculating the parameters, and the estimated model represent the entire population. Now, before reaching to this conclusion, we need to judge whether this alpha hat and beta hat are really following all the necessary properties that should a good estimator follow or not. Otherwise, how we will ensure whether from the sample we reached to some conclusion and whether this conclusion really present the population or not. Okay, so to understand this matter, or to before coming to the final conclusion, we need to judge the characteristics of alpha hat and beta hat. So one by one we will check whether beta hat is linear in yi, whether beta hat is unbiased estimator of beta, whether beta hat is minimum variance unbiased estimator of beta. The similar thing we will do for alpha hat, okay? The intercept term of the model. First, we are focusing on the gradient term, and then we will judge the quality of the intercept term too. So let's first start with the characteristics or the properties of beta hat, the gradient, the slope coefficient. So beta hat is summation xi minus x bar into yi minus y bar divided by summation xi minus x bar whole square. I'm denoting a term wi as xi minus x bar divided by summation xi minus x bar whole square. In general, in regression analysis, we consider xi to be non-stochastic variable, non-random variable. However, we should keep in our mind non-randomness is not at all a necessary requirement in our model. Okay. It is only a sufficient requirement. However, in general, while we develop the properties, etc., discuss the basic things, we consider xi to be non-random. So if I consider xi to be non-random, non-stochastic, the wi is also non-random or non-stochastic. Okay, so we are bringing one variable wi, which is equal to xi minus x bar divided by summation xi minus x bar whole square. So I can write beta hat as summation wi into yi minus y bar, which is summation wi yi minus y bar into summation wi, y bar into summation wi. Okay. In the next step, I'm writing this to be equal to summation wi yi as summation wi is equal to 0. Summation wi is equal to 0. Now, tell me how we are telling that summation wi is equal to 0 given the expression wi is equal to xi minus x bar divided by summation xi minus x bar whole square. Shambhav, tell us. Shambhav, I think you are there.
Yes, ma'am.
How we are telling that summation wi is equal to 0? Look at the expression of wi. Specifically, look at the numerator of wi. Are you getting any clue, Shambhav?
Ma'am, thinking. Wait.
Sorry. If I have can we say this is equal to 0?
Yes, ma'am.
Shambhav? Darpak? Aratrik told us yes. Darpak? Pratyush?
ম্যাম এটা তো তখনই হবে যখন মানে ডেভিয়েশনটাই দুদিকে ইকুয়াল, মানে পজিটিভ আর নেগেটিভ দুটো ইকুয়াল ডেভিয়েশন যখন হবে তখনই তো এটা 0 হবে।
এই এক্সপ্রেশনটা রয়েছে সামেশন xi মাইনাস x বার, সামেশন অফ xi মাইনাস x বার, এইটা 0 কি 0 না? সামটা অপারেট করো তো দুটো টার্মের উপর। Can we thing as? Can we write this thing?
Yes, ma'am.
So always summation xi minus x bar is equal to 0, isn't it?
Yes, ma'am.
Yes, ma'am.
So Pratyush, Shambhav,
Yes, ma'am. Yes, ma'am. Got it.
Yes, ma'am. Yes, ma'am. Yes, ma'am. Got it.
this is equal to 0. Yeah. So if we look at the expression, beta hat is equal to summation wi yi minus y bar summation wi. Safely we can write beta hat is equal to summation wi yi. Now if I write beta hat is equal to summation wi yi, basically what I am writing, beta hat is equal to w1 y1 plus w2 y2 plus w3 y3 and so on, plus. So if I can write this thing, can I write beta hat is linear in yi? If I write the expression beta hat is equal to w1 y1 plus w2 y2 up to plus wn yn, or beta hat is equal to summation wi yi, can we mention that, or can we express beta hat as a linear in yi? Can
Yes, ma'am.
anyone has any doubt? Everybody is okay with this? Beta hat is linear in yi?
Yes, ma'am.
Yes, ma'am.
Okay. So the first property of beta hat is linear in yi. Beta hat is linear in yi. The second property we will check whether expectation of beta hat is equal to beta or not. Whether expectation of beta hat OLS is equal to beta or not. If expectation of beta hat OLS is equal to beta, in that case, beta hat OLS, beta hat ordinary least square, is the unbiased estimator of beta, isn't it? Is it okay if I can show expectation of beta hat OLS is equal to beta? In that case, beta hat will be accepted as an unbiased estimator of beta.
Yes, ma'am.
Many people, I think, have any doubts. You know, are you understanding the matter? Everybody, Shreya, roll number 4, are you here?
Yes, ma'am.
Understanding the things? Are any
Yes, ma'am.
doubt?
Yes, ma'am.
Okay. If anyone has any doubt, please ask me. Okay, please ask me, because we did all these things in our statistics course, and now we are applying all the concepts when we are doing the econometric analysis. When we are trying to merge the reality with the theory, we are using those concepts. Okay. Now, on the basis of the data on price and quantity, you are telling that this is the estimated demand. So whether this estimated demand is universally accepted demand or not, that we need to judge. And for that matter, we need to check the characteristics of the coefficients. Okay. So now we are trying to understand what are the characteristics we need to check how really we can come to the conclusion, yes, this is the demand for orange. If these are the prices, if these are the quantities, in that case, this is the demand for oranges. And this is always acceptable. Okay, so this is the thing we are actually trying to do. So in the next step, we will check whether expected value of beta hat OLS is equal to beta or not. Will you do these things on your own? Will you like to check the property on your own? Now, what is the value of beta hat? We just did it.
Ma'am, in terms of xi and yi, or in terms of wi?
In terms of WI also, you can tell me.
Okay, ma'am. So then it is summation I runs from 1 to n, wi times yi.
This one. And if you start with the original value, then you can reach at this position, or directly, since already the steps are done, we can write this is equal to expectation of summation wi yi, where wi is equal to xi minus x bar divided by this is the ideal. Now, the properties, we know that is all in terms of ui. That is all in terms of ui. So always, somehow, in our analysis, we will bring ui. Okay, so always we will bring ui in our analysis, because all the properties, etc., or all the assumptions we have, that is in terms of ui. That is in terms of ui. Okay. So let me first show you the things. And so what we are doing, we are replacing yi by alpha plus beta xi plus ey. And then, as if you do this thing, you will be able to operate summation on each of the terms. So it will be alpha summation wi plus beta summation wi xi plus summation wi ui. Okay. So first I am writing summation wi yi. Then summation wi yi I am replacing by alpha plus beta xi plus ey. And then alpha summation wi beta summation wi xi plus summation wi ui. Okay. Just we learned summation wi is equal to 0, because the way we have defined wi, the numerator is becoming nx bar minus nx bar. So summation wi is equal to 0. So finally, it reduces to beta hat is equal to beta summation wi xi plus wi ui. So first you reach at this equation number 1. Please do the steps and check whether you are getting this equation number 1. If anyone has any question, any problem, please let me know. Could you complete up to this?
I'm almost done.
Hope everybody could complete it. So I'm moving to the next step. Now equation 1 has two components, beta into summation wi xi, and the second component is summation wi ui. So stop writing, look at the expressions. Now if you can show this summation wi xi is equal to 1 and this summation wi ui is equal to 0, in this case, in that case, if you consider expectation of beta hat, you will get that is equal to expectation of beta, which is equal to beta, since beta is a constant. Okay. So if the second part is equal to 0 and the associated component with the term beta is equal to 1, in that case, we will be able to show beta hat OLS is an unbiased estimator of beta. So one by one, we will handle the first component and the second component. In fact, for the second component, your task will be very easy. If you take expectation of the left-hand side, naturally you have to take expectation of the terms which you have in the right-hand side. Now, if you take expectation of the second term, expectation of summation wi ui, this will be equivalent to summation wi expectation of ui, because ui is the random component. So expectation will be operated on ui. So expectation of ui will be equal to 0, making the entire second term equal to 0. So let me check. So first I am considering summation wi xi. This is equal to wi xi I am writing as xi minus x bar plus x bar. So I am subtracting x bar, adding x bar with xi. So this is equal to summation wi xi minus x bar into x bar summation wi. So the first term is summation wi xi minus x bar plus x bar into summation wi. Now summation wi is equal to 0. So we are getting summation wi into xi minus x bar. Now what is wi? Wi is okay. So there is one more xi minus x bar term is there. So if I multiply this xi minus x bar with this xi minus x bar, the numerator is becoming summation xi minus x bar whole square. The denominator is also summation xi minus x bar whole square. So if I adjust the numerator and the denominator, we are getting this to be equal to 1. So summation wi xi is nothing but equal to 1. So plugging equation 2 in this equation 1, we get beta hat is equal to beta into 1. So beta plus summation wi ui. Okay. Now if I take expectation, it will be expectation of beta hat plus beta summation wi expectation of ui. Okay. Summation wi expectation of ui. since by the first assumption, expectation of ui is equal to 0, this expectation of beta hat is simply beta. Expectation of beta hat is simply beta. And therefore, we can safely argue that beta hat OLS is an unbiased estimator of beta. Beta hat OLS is an unbiased estimator of beta. Okay, and here you have one term, actually the explanation or implication is given. This is beta plus summation wi ui. Now in w we have xi components only. We have x only in w. So summation wi ui, that means covariance between xi ui divided by variance of xi. So it has been written in this way. The implication of summation wi ui. It is covariance between xi and ui divided by variance of xi. However, this is not that way related to deriving whether or checking whether beta hat OLS is an unbiased estimator of beta or not. So these are the steps by which we can prove that beta hat OLS is an unbiased estimator of beta. So look at the steps and tell me whether you have any question, any query for any term, any step.
Ma'am,
Yes.
I mean that step where we substitute 2 in 1, where we get that expression that beta hat equals beta plus covariance xi ui by variance of xi, that step. Ma'am, from the properties of the model, can we directly state that covariance xi ui is 0 from no autocorrelation?
Yes. Now here, you know, you have to express the thing as covariance xi ui divided by variance of xi. So we may not think about all this implication, etc. Simply mechanically too, if you calculate expectation, you will get the same result. Okay, Arathvik?
Okay, ma'am. Okay, ma'am.
Any other question? So everybody is understanding? So already two properties done. Beta hat is linear in yi. Beta hat is an unbiased estimator of beta. So next important property will be whether beta hat is a minimum variance unbiased estimator of beta or not. As you know, unbiasedness is not a unique property. You can have a series of unbiased estimators, okay? So we will not stop with this property, unbiasedness property. We have to move for one more property, you know, that is whether really beta hat OLS is a unique minimum variance unbiased estimator of beta or not. That we need to check. So that we will do in the next class. We will do in the next class. So please check the assumptions, estimation, and the first two properties of beta hat. First two properties of beta hat. Okay, check all these things. I'll talk about the minimum variance property, because minimum variance property has two parts. First, you have to calculate the variance of beta hat, and after that, I'll show you among all possible unbiased estimators, beta hat OLS is giving us the minimum variance. Okay, so it will have two parts. First, the calculation of variance, and then we have to show this variance is minimum compared to all other possible estimates. Okay, so that I'll do in the next class.